Northern Virginia's data center alley is the densest concentration of internet infrastructure on Earth. But right now, the utility grids supplying that region are fracturing under load warnings. Developers are responding by bypassing legacy hubs. Meta, for example, recently announced a $10 billion Hyperion campus, not in Silicon Valley or Virginia, but in Richland Parish, Louisiana. To see the new baseline for hyperscale, look at the physical footprint. Hyperion will cover 4 million square feet and is designed to consume up to 5 gigawatts of power. The catalyst driving this scale is compute volume. Meta is bringing 1.3 million GPUs online by 2026 to train their next-generation large language models. Powering clusters of that size triggers an infrastructure inversion. Network latency and real estate proximity used to dictate where a data center was built. Now, power availability is the primary metric. To achieve this scale, developers are abandoning legacy grid models. They are executing a geographic reallocation, pivoting to on-site power generation, and redesigning the underlying electrical architecture to run on direct current. By deconstructing the physical blueprint of a 2026 gigawatt scale campus, we can see how the industry is bypassing the traditional power grid. Data center growth is no longer achieved by building a higher volume of small, localized sites. The expansion is driven by a shift toward consolidated campuses. This chart shows expected data center sizes. The share of campuses requiring over 2 gigawatts jumps to 12% by 2035. Meta's pipeline tracks this trend. Their Hyperion project sits in the over 2 gigawatt tier, while Leap and El Paso sit in the 1 gigawatt row. In the physical world, a 1 gigawatt load is substantial. A single campus operating at this scale consumes 20% of the entire electricity load of New York City. Grid operators are preparing for this reality. ERCOT and PJM have revised their peak demand forecasts upwards by tens of gigawatts. But there is a structural friction point. Traditional utility expansion requires years of planning and construction, and it is moving too slowly to meet this revised compute demand. This chart details the disconnect in interconnection timelines across major U.S. markets. Green dots represent developer expectations. Blue dots show utility delivery. In hubs like Northern Virginia and the Bay Area, utility projections sit up to 2 years behind developer requirements. A 2-year delay is unacceptable in the AI hardware race. This timeline gap forces developers to abandon optimal network locations to avoid stranding capital. Because securing power quickly is the overriding priority, the map of U.S. data center development is being rewritten. This map illustrates expected changes in market share. Legacy markets like California, Oregon, Virginia, and Nebraska face significant declines. In these markets, aging transmission infrastructure and permitting complexity have become liabilities for scaling AI inference. The new geographic winners are defined by raw power availability. Texas projects a 142% gain, pushing toward 40 gigawatts. Plotting Meta's newest projects in Louisiana, Indiana, Alabama, Texas, and Wisconsin, they align exactly with these growth regions. Hyperscalers are executing this geographic pivot now. Developers are sacrificing geographic proximity to end users. They are building in these regions because they offer a faster, guaranteed path to power. Changing zip codes is only a partial fix. When a campus requires 2 to 5 gigawatts, it eventually exhausts local grid capacity. To guarantee speed to market, data centers must internalize their own power generation. This graphic tracks developer expectations for fully on-site generation. By 2030, the industry anticipates a 22% jump in the share of data centers detached from the utility grid. Meta's El Paso facility is executing this model today. That campus relies on a proposed dedicated 366-megawatt natural gas plant built to power the site. This data breaks down the technologies developers are evaluating to bypass grid delays. Notice the 47% evaluation rate for fuel cells. Fuel cells are preferred for shorter lead times and modular scalability. They produce lower emissions, bypassing the permitting bottlenecks that delay traditional substations. Bringing power generation on-site requires a redesign of how electricity moves from the generation source to the server rack. This chart outlines plans to adopt next-generation electrical distribution designs over the next 2 years. By 2028, 60% of respondents expect to adopt high-voltage central busways, and 45% will implement direct current architectures. The mechanics are straightforward. Traditional data centers pull alternating current from the grid, requiring multiple conversion steps to deliver direct current, resulting in heat and energy loss. An on-site fuel cell produces direct current natively, feeding a direct DC busway straight to the server. By eliminating those conversion stages, DC architectures reduce excess heat and deliver the stable, high-density power required by AI GPU clusters. When you integrate on-site generation directly with DC architecture, the campus functions like a highly efficient industrial plant. Small data centers plugged into centralized grids cannot support these compute loads. The reality of 2026 is the 2-gigawatt self-contained microgrid. The new infrastructure blueprint relies on 3 pillars: moving capital to power-advantaged geographies, securing permanent on-site generation, and redesigning internal architectures for gigawatt-scale efficiency. To build at this scale, developers must also engineer efficiency into their resource consumption, deploying dry cooling technology and water-positive restoration goals to satisfy local municipalities. Operators who rely on traditional grid assumptions and legacy hub locations will face timeline delays and stranded capital. Power is no longer a downstream utility consideration to be solved after picking a site. Power availability has become the defining constraint on growth, and the data center has transitioned into an independent power plant.